very cool stuff. So it's always good to hashtag spread the knowledge. So let me just share my slides. Okay, I cannot find my slides. Okay, they're here. I mean, copy. I think from my point of view, like this is like to do this. So let me know. Apparently, PowerPoint is preparing my slide. Let me know when you can actually see my slides. Okay, so again, welcome to everyone. This pizza session is gonna be about transformers. So I don't know if you have heard about that. It's actually a topic, and more than a topic, an algorithm that has been like out for many years now, but just got really trendy over the last 2-3 years after a paper was actually considered important. The original paper is called Attention is All You Need. And now we are going to analyze how a transformer works. So just gonna give you a background because the transformers, and sorry for the nice image I put here, but yeah, I had to. So transformers is a kind of descendant of some other algorithms, let's say. So it was important mostly for if there is someone that is not extremely technical to give a kind of background, in like deep learning, basically which one is the field where the transformer belongs to. So second part, I'm going to give a kind of step-by-step high-level explanation because yeah, this is an extremely, and I will say again, extremely technical technical topic. So also considering that it's going to be 2 hours, I try to split this in a step-by-step higher-level explanation. So the most useful information that people will need if to understand actually what a transformer is, how it's like what are their parts, all this kind of stuff. After we have, and yeah, I jumped one number, I don't know why. After we have a kind of in-depth analysis, so basically it's gonna be a real kind of math related analysis. This is for those people who like pain and math. So I just put the specific section there. After that, we're going also to analyze one of the use case where transformers is used, like abstractive summarization. And I'm going to talk about one of the most proficient, let's say, state-of-the-art algorithm that does that, called Pegasus. And this is going to be the end of the slide. So the sixth, actually should be the fifth part, fine-tuned transformers. So I prepared the Jupyter notebook because actually we are not the company that is able to train a transformers from scratch, but I will show you how to fine tune one. And this is going to be extremely helpful as long as you have a good amount of data, extremely helpful and extremely high performance. So you can use it in kind of NLP project, but also can be applied in a computer vision project and so on. So let's start because we have many slides to present. Okay, let's start with a bit of background. So tasks in NLG, natural language generation, are best expressed as, let's say, sequence-to-sequence problems. So as you can see here, we have an input sequence like word input 1, word input 2, word input 3. We apply a kind of function, and this produce an output that it can be same length, it can be different length. So think about when you use Google Translate, it's basically what we do. So if we use one language and basically we try to translate something that can be made of, a sentence can be made of like, I don't know, 10 words, the translation is not necessarily as long as the input. So what we have to do is finding a function that basically map the input, X, into the output. So pretty easy. Actually easy just to define the problem. So again, the sequence prediction involves basically historic sequence information to predict actually the next value or next values. So this is used also in music generator. So you basically start from some notes and based on a training set, you actually try to predict the next node. So it's used also. There are some songs on YouTube which actually are made entirely by AI, text captioning, and also image generator. So as you can see, the sequence-to-sequence problem, it can be applied to basically the majority of the tasks that you can resolve with the deep learning algorithm. So the architecture that we are going to analyze is called encoder-decoder. So what it does in encoder, it takes a variable length sequence as the input, and basically, given this sequence, it transforms into a fixed shape. Let's say middle input. Let's call it this way, because after the decoder, actually use the laser, yeah. Because after the decoder, what's it doing is it maps whatever the output is out of the encoder state, that is fixed shape, to a variable length sequence that is the output. And use case can be, as I said earlier, translation, paraphrasing, summarization. So are all these cases that when actually, we don't know the output length a priori, but the output length can be variable, and again, necessarily is not going to be as the same as the input one. So deep learning model, they actually, such as RNN, LSTM, they are able to handle sequence-to-sequence problem. So for example, here is an LSTM model. We actually use as well encoder-decoder architecture. This is for like translation. So weather is nice in English. This is French, yeah. Is whatever is written there. So basically, and again, the encoder, so the first part, encode an input to a fixed length internal representation. The decoder, what it does, use this representation to output the words until it's predicted this, that is called special token. So this stop, it basically just means that we have reached the end. And I will show you after how to set up this stop. We also have this start, that is, it indicates the beginning of the sentence. It also has a specific task. So what else to say? Yeah, here we have, just to give you a bit of additional information, we have the internal state of LSTM that is defined by H and C, where H is called hidden state output. It basically has the encoding of the most recent time step. And C is the cell state output, that basically is the global memory, because so LSTM, it's a kind of RNN improved because it implies some memory gates to be specific, and so on. So next, okay. So what we do, how the RNN work, because in order to understand why we have to use the transformer, we have to understand why the other algorithm, they don't work. So during the inference, what it has, the encoder, we have an input here. So is, again, this is a translation task. So is I want to buy a car in English, and we want to translate in what I think is German. Yeah. So during the inference, the encoder encodes all these the raw input, and update the hidden state. So when actually all this processing is finished, all the encoder, we have something that is called C. So is the cell state output. And so basically the function of the encoder is basically just to try to produce this C, this internal representation, starting from a raw input. So the first part is done. So basically the encoder is just using basically the beginning. So after we get this C, we basically start using the decoder. So the decoder is used in autoregressively way. So it means that autoregressive means that you use the past to predict the next values. And so in order to generate the probability distribution of a target sequence, that is basically, so this is the conditional probability distribution that given y, so the probability that the output is yi, given everything that is come before and c. So in order to express this in a kind of simple term, given the previous word, for example, if you want to calculate this auto, so which one is the probability that the next word is auto, given that all the previous word has been this one plus C? So basically, again, is using the past to predict what is going to be the next one, the next values. So all this looks good. And again, if you have any question, because there are a lot of topics and stuff, feel free, Suzanne, to stop me and I can answer to everyone. It's better to answer to the question straight away than like waiting the end. So everything looks good and fun. The problem is why we need the transformers, because this looks to work already. So we need the transformers because the main problem is about retaining. So the main problem of all the previous architectures, RNN, Lstm, that also was supposed to fix this problem. This problem originally arose in the RNN, that is recurrent neural network. So it's about retaining information far in the past. And I prepare a kind of silly example, but it's not so silly. So imagine you are running a marathon, and I don't know, before starting the marathon, you actually you eat a nice plate of fish and chips and a pint of beer. I would say Moretti because it's the unique one I drink. So the problem is that after 30, 40 kilometers, the network has forgotten that you ate that. So it's not able to understand and to predict the next values because is losing information regarding the first elements. So again, main problem is try to remember everything and not just the most recent information. And so again, here is explained in a better way. So in the encoder, the hidden state that remember is this H in every step is associated with a certain word in the input sequence, usually is one of the most recent. So the decoder, we actually feed the last hidden state of the encoder. So the decoder does not have information about what is happening at the beginning. And so this is actually the main problem. So what we need to do, we need to expand our view, considering a bigger context when we want to generate the output. And so in order to do this, we use a mechanism called attention. So the attention mechanism, I will just give you a brief summary here, what it's about, and I will explain in better detail later. So the attention mechanism, so the idea behind this was to permit, again, to the decoder to utilize the most relevant parts of the input sequence in a kind of flexible manner by kind of weighting a combination of all the encoded input vectors with the most relevant vectors being attributed with the highest weight. So if we see here, we have the word eat. So let's say the darker is the color, the more weight has this word in relation with it. So when we say eat, we actually refer to the animal. And basically these two words are the one actually we are the most, let's say, colored, because in the internal representation, when you actually want to predict the next word that will be coming after it, you need to reference to actually the input words we actually affect the word it the most. So in this case, it's going to be the animal. But again, I will explain this in better details later as well. So this is how a transformer looks like. So basically, again, in this step-by-step explanation, we'll give you the main steps and the main characteristics. And I'm also going to analyze separately the encoder part, the decoder part, try to understand how they really work, like, let's say, behind the scene. Okay, so the transformer-based encoder is the green part. The decoder is the red part. So again, in this case, let's take this example. We want to translate the English sentence, I want to buy a car, to German, yeah, whatever is written there. So every word is, like you can see here, there are like multiple rows, one for each word, is embedded separately and fed to the encoder. Plus something that is called EOS, that is end of sentence. So it's a special vector that basically is indicating that the sentence is finished. When we go, the decoder is the red part, And we also have here something called BOS vector, which actually means beginning of the sentence, which represent the input vector y0 that is fed to decoder at the very first step. But again, I will give you a better explanation of what this means. Next slide. Change. Okay. So first step, again, like I said, is about processing the complete input sequence. So we have X, we have X.
Nunzio,
Yeah.
There's a question from
Yeah.
someone. Someone raised his hand.
Sorry, it's slide 15. I have a question. Why do you have why there are vectors on the top of on the previous slide 15?
Sorry, say again.
On the previous slide 15.
Previous slide.
Yeah,
Yeah.
Here. Why on the bottom you have its word, but then on the top you have vectors. What is inside each of the vector?
So basically, because actually the machine doesn't understand like what the word is. Every word is basically a vector that actually is at the beginning. You actually get some pre-trained model on words. So just to give an initial representation of how the word looks like. So basically every word is a 256 based on the architecture, 256 or 512 dimensional vector.
Mm-hmm.
So imagine every word is like a point in a very high dimensional geometric space. And you know, when you listen about problem or you read about problem about similarity, it's just about how close this point, and every point represents a word, how close they are in this very high dimensional geometric space. Because actually the computer doesn't understand the word has like letters, but we have just tried to, we normally say embed the words in a kind of vectorial representation.
So so for example, you use something like word to vec for
Exactly.
single. Okay, thank you.
Exactly. So you can actually, so there are different kind of a way of doing it. You can give like like to start, you can give like a kind of a random representation, or you can use some other model. So depends, there are like different kind of approach.
Thank you.
So I was here, yeah. So first step, again, is about processing the complete sequence. So again, these words, we actually need to, they are embedded. So again, creating this vectorial representation, and they are contextualized. So to X, so I put hat here, so X at. So for example, X for at defines an encoding that depends not only on the input that the raw input that basically is the word by, but also on all other words. So I want to car and EOS. That is basically the context. So because actually what we want to embed word, we also, because actually word can have a different meaning. So we also want to understand, you know, what is around this kind of word. So we actually we want to extract the context. So after we do that, we input this internal representation that is the output of the encoder with the BOS vector. Again, this is a special vector that is indicated in the beginning of the sentence. These two are fed to the encoder. So it processes the inputs. So for the first step, it processes all the internal representation plus the BOS to create the first logit. So a logit is basically a vector containing all the prediction that is not normalized. So it just a specific term that normally is used. When actually you have a logit, is extremely likely that you will get something like softmax later in order to normalize all the prediction. So just to explain this in mathematical terms, so the probability of having of calculating, let's say, the first word, actually the probability distribution of something being like specific word is given by it's basically a conditional distribution where we actually want to calculate y, and a priori is known the BOS and basically all the encoding representation that is actually the output of the first part. So it's actually with this formula. So again, in order to understand, to calculate the next values, you basically use all your memory. So what you have calculated until that time, and let's see if this can help in some way to, to calculate again the next step.
Yeah, definitely.
So when we calculate the first target, which is the first target vector is each, I don't know, because what we do this is during training time. So what we want to do, we also have to give in input, you know, the ground truth, the label, because in this way we are actually able to map, you know, the machine is able to understand that to this input is mapped this output. What we want to do, we want to create a function that will do that automatically, so without us telling, you know, which one is going to be the output. In order to do that, for the training, we have to tell them, you know, what the output is. So this is a classic, I would say, classification problem, a little bit more complex. So again, for the other word, we'll do exactly the same. We'll use, in this case, for the word each. So this is the first one we actually calculated. To calculate the next one, we now so before we had in input just the BOS, the beginning of the sentence. Now we have in input BOS and ish. So again, every time our memory is updated, and so every time you have more data to calculate the next step. So in this way, with all this more data, you will shape a better context to what is coming after. And so to calculate, like, this is the end, the last token, EOS, that is end of the sentence, the formula is going to be this one. So again, it's a probability distribution, it's a conditional probability distribution of calculating y, the probability that y is equal to EOS, knowing that before we had all these words, and we also had again the output of the encoding. So I don't know. Hopefully, if it's clear, more or less. If you have any immediate question, just again feel free to ask me, because now we are going in a kind of more details. So again, it's a very thing that is important to understand is that the encoder is normally is only used in the first forward pass. So basically to map the raw input to this kind of internal representation. You can think as mapping from real words to a vectorial representation that will also take context into consideration. The decoder is actually what we use for the step 2, and it can make use of, you know, all the previously calculated encoding. So again, this is this is step 1, where actually, so we go from bottom to top. So basically in this way, and after this has been calculated, this is passed to the decoder. And so all these kind of prediction, they are like stuck together, and they are passed to every different step of the decoder. And I will explain after what all these steps are. So here, I think, yeah, so here, hopefully we have a kind of general overview of how a transformer-based encoder-decoder model works. Because from now on, we actually are going to deep into the encoder-decoder part of the model. So more specifically, because if you remember the beginning, I said something about attention. So more specifically, we actually see how the encoder uses this kind of attention mechanism, and basically how to in order to yield a sequence of context-dependent vector. Because what we do here, we pass from an independent context vector encodings, because like I said, we just get this word. There are like multiple ways to initialize these vectors. I was just reading a question. So I will show you also in the notebook, every punctuation, every character, they have a specific representation. So even if there is a dot, that dot is not going to be EOS. EOS is a specific special token that is not trained. It's like kind of a flag. So yeah, coming back to the slide. So yeah, we pass from an independent to a dependent one. And basically, in order to do this, there is a layer that is called self-attention. And we are going to see how this self-attention layer works. So as I mentioned previously, that basically the encoder is just basically a mapping. It does a mapping operation. So we have a function of theta of the encoder with this kind of parameter. So we get kind of argument. So basically we get a kind of raw input. So x1 to n, that is basically all the words. And we're just going to get a context-dependent representation of those words. So two concepts that you should know in order to understand what is coming after. So the whole encoder section is a stack. So as you see, coming back to one slide, it's not just one, there are three, but in the original implementation, there are 6 of them. So it's basically a stack of something called residual encoder blocks. So again, like I said, there are 6 in the original presentation, and each encoder, each block consists of a bi-directional self-attention layer, followed by 2 feed-forward layers. So again, just give you a brief intro what the residual block is. So basically, in next slide, in neural network, each layer feeds into the next layer straight away. But in very big network, we actually contain hundreds of layers in order to, let's say, to transport the information from very deep layer to shallower layer. What you do, you basically just skip some layers. So as you can see here, the input, it doesn't go through these 2 layers, but basically just skip these 2. So in this way, we can actually bring the information to the last part, to the latter part of the network, and we have a better understand. There is a better training with using this method. The second thing is what a bidirectional layer is. So bidirectional layer is actually when we see both past in time and forward in time. So this means that in neural network, basically, when we try to learn from seeing what it has happened already and what is going to happen. So we basically see in both directions, future to past and past to future. So in simple terms, for example, if you want to get the representation of his, we just see what is coming after is and what has come before is. So this is what a bidirectional layer is. Okay, so let's start with the encoder. So again, this is pretty, even when I had to study this a bit, it was kind of pretty hard to understand. So the self-attention layer puts each input vector. So remember, when it's actually first, so we actually start from, just for explaining you the syntax that I use. So when we start with the raw input is basically just X. So when the input is processed through the first block, it becomes X first, second block X second. So the self-attention layer puts, imagine that we are here, so we've done the first block already. So put each input vector X first into relation with all input vector from 1 to n, like you can see here. So if you are confident with neural network, this is kind of a dense layer. So everything is connected with everything else, like you see in this case. There are all connection, and this is what bidirectional means. So basically, x2 is connected with x1, but it's also connected with x4, x5, x6. And we do this in order to get a more refined contextual representation. And this refined is called X second. So because actually we have 6 in the original presentation, it should be X first, X second, X third, and so on. So the more you go inside this block, the more block you do, the more contextual refined is the representation. So basically X first n is basically just to indicate the last element. So if I want to, otherwise I should have written like everything x1, x2, x3, x4, 5, 6, 7. You just put x first con n just to indicate the last element of the list. So let me see if okay, now the real kind of hard part is starting. So until now, probably you kind of have all the information to be able to understand what more or less a transformer is. This part that is starting now is basically the kind of very deep part. So how self-attention is calculated, how it's going to affect the output. Okay, let's start. So let's take a deeper look at how this famous bidirectional self-attention works. So so each input vector x first j, and so by far should be clear to everyone what xj is. So it's of an encoder is projected to three different vectors. One is called key vector k, and you have it here. Is the yellow one. A value vector v, the blue one, and the query vector q, that is the violet one. And in order to calculate this, you have like three weight matrices. And these, as you can see, there is no like I, j, or anything. So these weight matrices, they are shared across all the input. So, next one. In order to calculate, and just for now, bear with me, just try to read this sentence, even if you don't understand, it's fine. In order to calculate the attention with the query itself is compared with keys and gets score or weights for every values. So each score and weights represent the relevance between the query and each key. And using this product, we basically reweight the values and take a summation. So it's a bit art, probably. Let's try to see with another example. So we have this sentence: Anthony Hopkins admired Michael Bay as a great director. So what here happens is that a query is basically a word of the input. And what we do, we compare every query with the keys. It is likely that, for example, the token Michael has a biggest weight score because, of course, is compared with itself. So in this way, if you just like, let's switch off all the machine learning stuff. So if we want to think like a human, what we want to do, we actually want to say, okay, how close the query is to all the other words. And it's called self-attention because, as you can see, you basically compare the text with itself. So we are comparing the text, not with another vocabulary or another stuff, but with the same, with itself, the same words of the same sentence. So we basically, in this case, we just see how Michael is affected by everything else, by all other words. And again, for example, director might also have a big score depending on a standard of calculating attention using like Michael as director. Because in this way, the machine is going to understand that, okay, director is referred to Michael Bay. So when there is director, is probably also the weight of Michael Bay being the next word. It can be higher than the word like Hopkins, you know. And of course, like I said at the beginning, the tokens are embedded vector in practice. So after you have this, you calculate this kind of product, you reweight the values. So every word, at the end, every word will have like a single representation. This representation will be given by all the weights that have been calculated comparing the query with the keys. So yeah, this is the kind of a high level of how this works. Let's see a kind of example. So assume that the query is the token Michael. The weights of the key tokens like Anthony Hopkins admire Michael Bay as a great director. Imagine that these are the weights. So what we do when we want to like I said before, reweight the values, these values here, we basically just do a weighted average, because so this is just basically saying that if we analyze the query Michael, we have to reweight the token. So we have to see the token from a different perspective, considering that Of course, words like Michael itself, that is the same word, it will have like a bigger weight. So again, it's just trying to understand the context. So which word is more affecting for which other words? And so just going back one sec to the attention slide is actually what we have here. So in this case, it has more, so the and animal, when we want to actually get a representation of it has more weight, so should be considered more than other words, because in this case, the and animal, they are referred to it. So going back, so we do this for every different query, so every different word in the sentence, and at the end, so when you do D, you basically repeat all the process, and you get a stacked summation of the reweighted values. So stack summation is going back to the original image. After we do everything, we basically just get a summation of all these x second j of the output of the encoder. And so again, it's very important to understand this concept. And again, feel free to ask me all the questions because there are no silly questions. So again, there are three concepts to remember. So we have the key, the query, we have something called keys, and we have something called values. So what we do, we use the query and the keys to update the values of the words. And also to give you a kind of analysis dimension analysis of how this looks like. So don't see this decay was just for us like for normalization, so we don't need to see this now. So again, the query is 9 dimension, 9 rows, because it's one for every word. And for example, in this case, every embedded vector is made of 64 different dimensions. So again, every word means, so literally means that every word is projected is in a 64 dimensional geometric space, and is basically a single point in this space. So when we multiply the query by the key, we'll basically get, we basically do the softmax. To normalize, we basically get the how related are a specific query with all the words, and we use this product to update the value. So again, at the end, every word, the attention of key QV, it will be basically a single updated embedding vectors, which will be completely different by the beginning. And the unique difference will be that now it also has context in it. So again, we pass from an independent context representation to a very dependent context representation. And this dependency is calculating when we multiply by Q and when we update the V value. So hopefully is kind of clear. We'll just give you maybe some seconds to figure it out. And again, if you have any question, just feel free to ask me. Okay, so now just like reviewing all the process, what we do at first, all input vectors are projected to these so-called query vectors, Q1 until Q7. Only the first, in this case, only the three are like shown in purple. So, but also the other one will have the same structure. So again, purple one is the query. In orange we have the key, and in blue we have the value. And these are like so we basically do the product between the key and the query. We do softmax. And I will explain you why we do softmax is because when you actually predict, you have all this kind of vector, but it doesn't. Let's say all the probabilities they don't add up to 1. So we just want to normalize and get everything fit in order to also apply in future in metrics and stuff. How do you compare case against the query? So when you actually, so it is actually what a very long training is doing. Because so what it does it's like, so we have the query, and basically where we get the key. So at like practical term, the comparison is basically just comparing the different vector between the different words. And at the beginning, some words they may not be related, because the problem is that we don't have a kind of pre-trained memory. So it's basically like when you study a book, the first time you see something, you probably don't get the most of information, but using like training on several different epochs. So just to give you an example, the GPT-3 that is the best for, I think is text summarization. So the training time was like 3 weeks. So basically 3 weeks training on a very good machine, and the cost was around, I think, $3 million just to train the model, just to get this knowledge. So again, what we do to compare is basically just like comparing the vector and see how close they are. And this vicinance is also, this proximity is also given by the fact that we have been training the machine for a long time. And so after a long time, we are seeing actually the results of, extrapolating the context from these words. Again, going back, and at the end, what we do again, value multiplied by the softmax product of Q and K, and we also sum the previous input. And again, at the end, just one case, at the end of this, we'll get a very refined representation of every word. Again, I'm getting again as example the word want. Again, starting from the very input layer where the word want doesn't contain any context. We go through a different encoder, and also another important point to spot is that there are, so as I said, there are 6 of these, and so all the processes I trying to explain you, hopefully clearly, it goes through all these different blocks, so it's repeated 6 times. And basically in this way, like this repetition is trying to make everything more robust. So starting from X where the context is basically is not there. Again, we have X first, X second, and by the last one that in this case is going to be X third, but normally it's like X6. We basically get again a very context related representation of every word. And again, being bidirectional means that it's getting the context from what it has behind, what was behind in the past, and what it has in the future. So I get like a very complete context. So hopefully the encoder is clear. Now let's check the decoder. So again, as I said previously, the decoder defined the conditional probability distribution, of a target sequence given the contextualized encoding sequence. So again, we get everything that is coming out from the decoder, so all the bidirectional stuff, attention, blah, 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 blah. And using that, we try to calculate the Y. That is, if it's a translation, we actually try to calculate, what is actually that word in the other language. If it's summarization, it's a kind of a different process, but very similar to this. So it's based on the task, what output we're going to calculate. So just for the math lovers, using the base rule, this conditional probability distribution can be decomposed in a product of conditional distribution of the next target, given again the contextualized encoding sequence and all the previous vector target vectors, so all the previous Y that we already calculated. If you see the formula here, just for now, just don't see this, because this is just like a multiplication. So what we do is calculate the probability that the next word is, I don't know, sun, given all the previous words that we calculated already, plus the encoding sequence that comes out from the encoder. And so, again, the decoder has a very specular structure of the encoder. So again, is a stack of decoder blocks followed by a dense layer that is called LM head. So what it does, again, the decoder blocks maps the encoding, again, the output of the encoder and a target sequence. So this is the ground truth. So again, just for an info for clarity, so the ground truth is indicated by Y. The predicted output is calculated by what is shown by Y hat. So when I say Y is the real label, when I say Y hat is basically the label that we are calculating. And so what we do, the decoder again maps the contextual encoding and the ground truth prepended by the BOS vector, so beginning of the sentence, to an encoded sequence. So this is actually the calculated one. So what we are trying to calculate. After we do this, because again, we have this kind of LM head, what it does, it maps the target vectors to a sequence of logit vectors. And remember, the logit is, let's say, the unnormalized version of the prediction. And so the dimension of each logit is basically the dimension of vocabulary. So imagine in our vocabulary, we have 1,000 words. Doing this process, we are just saying what is the probability that the output word for this is actually Y1, so it's the first one in the vocabulary, or the second or the third. So we're just calculating the probability of the output being any word that is in the vocabulary. So for this, we have the logit that is as big as the size of the vocabulary. So as you can see here, start from Y1 arrives to Y vocab. So, but just basically calculating probability of every word. So, so what we do, first step, there is actually on the right side of the process, real first step. So probability that Y is a certain word, and again, we scroll over the vocabulary. Y is a certain word given the BOS, that is the first vector, so beginning of the sentence vector, plus the contextualized encoding sequence, that AKA output of the encoder. So this is the first step. Imagine that we calculated that the first word is each, is correct or is wrong, whatever. For the second calculation, for the next word, that is will, because actually this goes in this way. So we have, so it goes down to top, 1, after that's 2, 3, and so on. So for the second calculation, what we do, we use, instead of using just BOS, we're using BOS and ECH, I don't know. Because actually now we know that a previous target vector has been calculated already, so we can use that knowledge in order to improve our next forecast, our next prediction. And again, always we use the encoding sequence. So yeah, just but again, for clarity, this is a kind of a conditional probability. So it's probability of calculating something, knowing that something else has already happened or is given or is basically just true. And so the last one will basically be, so the last one should be EOS, is basically be all the probability that, you know, knowing that we have this sentence and knowing that we have this input, let's check which one is going to be the next word. And because in theory, if it's well trained, we have put the context, so the machine will know that there is no next word, so the sentence is finished. So we'll just output EOS. That is, it basically means end of sentence again. So this is how the decoder works. Let me see what I have here. Yeah, and again, the self-attention mechanism, that was a kind of very high level. Self-attention mechanism works in exactly the same way, but just for one single difference. And now I need you guys. So just one single difference. So the encoder is a bidirectional self-attention that, if you remember, is tracking information from the past and from the future. But then the decoder is a unidirectional self-attention. So someone can tell me why is that? So again, bidirectional check both directions, what is happening. But the decoder that we use to calculate the output is not checking both directions. It's just checking one. Can you tell me, because it's unidirectional, can you tell me why this happens? We'll just give you 5 seconds. And maybe, I don't know, a panettone for the one who guess when I go back from Italy. So if you think, so bidirectional, again, it's not speed, it's just for something very logic. So when you imagine that you are preparing for an exam and you want to learn, you are studying, you basically will study, if you want to study in a very cheeky way, you will study the question and the answer, because you will get everything, you know, all the maximum information you want. But when you are on the exam that you want to, let's say, predict the output given the question, you cannot know what is coming after. Otherwise, you are just introducing bias. So if the decoder was bidirectional, this would just mean that in order to calculate that the next word is, for example, sun, we are also giving into training that the next word is sun. So the machine will just learn about mapping the current input with the next word. It simply will not, you know, will not like give us any model. Actually, it will be a model, but it will not be working because we'll just be able to, it will just be basically a mapping. So unidirectional means that it's just checking on all the previous words and not like the future ones, because the future ones are the ones we want to calculate. So no panettone for you guys, I'm sorry. Okay, so summary now. So I basically this is how, again, how the transformers based encoder decoder model works. And so again, imagine 6 blocks for everything. You have self-attention here. Again, self-attention is actually what is missing from the previous architecture. Is actually what is used to give a more refined context to the words. As soon as this has been done, all this is sent to all this kind of information is sent to all decoder part. The decoder part during the training, will use all the, basically all the real label, the ground truth, and actually using all the past information and output from the encoder, we'll try to predict, in this case, the which one is going to be the next word, the next translated word. And I think, yeah, so this is the end of the transformer, the encoder decoder, the transformer based encoder decoder model explanation. And yeah, basically, I don't know, I'm moving on to one of the use cases of transformer, that is abstractive summarization. So if you have any question, like immediate question, just write in the chat, or if you have any offline, let's say, question, you can just like ping me when I'm offline. And by the way, there are also kind of other mechanism. So the transformer is also very good because it's able to parallelize everything. So there is also another kind of attention layer between encoder and decoder that is called cross attention, but it was actually encoding. Yeah, exactly. Yeah. So encoding, again, it's just trying to, because again, like neural networks, yes, like neuron is an axon, so just to establish, you know, any kind of correlation between words in some way, just to say that, I don't know, if I say the word machine and I am in a technical concept, the next word probably it can be learning, so all these kind of things. And decoder is actually what is producing the output. Even for this, if someone who has ever used BERT, that was probably one of the state-of-the-art for word embedding, BERT was just contained an encoder part and not decoder, because actually the main task for BERT, the main goal for BERT was just, to create a very robust representation. And we know with like all the word, getting all the different like links to other words, basically getting all the context and just have a very context refined representation of every different words. Yeah, sorry for repeating words many times, but yeah. So yeah, again, encoder, decoder, this is probably the next. So is extremely expensive to train, but it's gonna be probably the model. It's actually able to resolve any task with this. So time series, computer vision. How would you represent your X? So I guess that the X you refer to is the input. So again, normally you can use many different techniques. For example, because like I explained earlier, you have like attention. So again, every at the beginning, when you want to initialize the attention value, you just like put random value or normally put 1. So again, even in these, you can just get a normal basically representation from some other models, or you can just get a kind of standard random representation. But like you 100% if it's random, it will take like more time to train and more time to reduce the loss and more time to increase the performance. And there's already a lot of time that you need to train. Do multimodal transformers? Yeah. So again, what I explained there, it's basically the first release, let's say. There are like so many different structure, and the multimodal transformers is probably one of the most complex, because it also has a different kind of attention mechanism, many more layers, because normally you have 6, but you can have in like 10, 15. And when you actually increase the layer, it means that all the attention process, he has to go through all the layers. And by the way, one thing I try to forget, the self-attention layer that is happening, the bidirectional layer that is happening inside one block is not 1, but there are like 8 in the traditional representation. So even if there are 6 blocks, every block contains 8 layers. So it's going to be 48 layers for the encoder and 48 layers for the decoder. So we reach like already 100 layers. And it's so one of the main problem with this is what I said at the beginning. We don't have, as PA, the capability for training something from scratch, not because we're not clever enough, it's because we don't have the machine for doing that. Because the cost, if we want to do it on cloud, the cost will be basically enormous. Okay, so let's start to talk a little bit about something new, because we have seen translation until now. By far, now we'll see abstractive summarization. So normally, is actually what I do. Given long documents, is basically is not very cool to to read everything. So what we tend to do was like human, we just try to scan very quickly the main points. So for every document, so long document, having a summary would be great in terms of like saving time and also brain processing power. So before the kind of sequence-to-sequence model, the auto summarization was extremely challenging and almost impossible to achieve. Because again, one of the main prerogative for like deep learning models is that you have also always to fix the output. And you can also, sometimes you have to pad if the output is too long. So it gives you too many restrictions. And also you didn't have the right architecture to build something like summarization. So we normally have 2 types of summarization. So we have extractive. So extractive is basically just like extract important sentences from a document and combines them from a summary to form a summary. What we are going to focus now is abstractive summarization that involves also paraphrasing words and basically is more difficult, but also can give you a more coherent and polished summary than just like stacking up, multiple sentences. So an example here, this is a document. This is basically what the extractive summarization looks like. So it's just getting the blue, let's say, small paragraph, and so that is the summarization. But in this case, you can lose some information that is somewhere else. What we're going to focus now is that is more difficult task, abstractive summarization. So it's, as you can see, there are not like many words like this in the document. So you're just trying to, we can say as we can just like to read the document very fast and get like a semantic close summary, but not like the syntax is completely different. So again, like I said, until like the sec-to-sec sequence-to-sequence model, an unsupervised language like Elmo or BERT, that abstractive summarization became more feasible. So what we are going to analyze now is something called Pegasus. And so Pegasus is by far the state of the art for summarization. And I will also show you how we can actually fine-tune Pegasus. I will explain also what fine-tune means. So very quickly, again, it's encoder-decoder representation. So the input is, for example, Pegasus is a mythical creature. We create the context vector. So this is the output of the encoder. So the decoder will get the real summary and also the context vector. So pretty straightforward from here. But the problem here is the main challenge is collecting training data, because this is still a classification algorithm. So you need to provide the labels a priori, let's say. So we have to collect the training data. That is not very much about collecting document. The bigger problem is to create a reference summary that, we are talking about millions of documents here to train from scratch. So how actually we can do that? And also transformers being deep learning, but is also quite, let's say, data hungry. So we'll need quite a lot of data to train. So these are the previous state-of-the-art model that were trained on this specific task. So we have CNN with 90,000 documents. Dataset, they use dataset like Daily Mail with 200,000 and these other datasets. So how we can get close, like me being a single data scientist PA, how can I get close to this state-of-the-art without, wasting time about collecting data? So, yeah, that is, you stole me one of the of the key points I wanted to explain, because yeah, Hugging Face is one of the best repo where actually you can get many pre-trained model, you can get many different datasets as well, and how will show very soon how that looks like. So yeah, Pegasus, completely open source. If you have time, I mean a lot of time, you can actually see the GitHub repo of the implementation. And is developed by Google, of course, state of the art for the paraphrasing task. So Pegasus originally, so it's not something that is close to us, originally from scratch, was labeled on 350 million of web pages and 1.5 billion on news article. So now I want to explain, because I said like training from scratch or like fine tune. I want to briefly explain what that means. So pre-training is basically when you train from scratch. So you train actually, you imagine you are like filling an empty brain with knowledge. Fine tune is actually when we want to use already that knowledge and we want to tune the knowledge on our specific task. So that is the main difference. So what we do, the idea here is to label every document using some important sentences which closely resembles what abstractive summarization needs to do. So in order to generate important sentence, we will use the other type of summarization that I don't have the name now. So we have to extract this sentence from the document. And so this is going to be our labels. And in this way, and given all the input, the model is able to create abstractive summarization. So now one point, so this is going to be the label. So now one point is how we calculate that. In order to calculate that, we use something, a metric called rouge. So assuming we want to choose, for example, one sentence as a label, we just get the top one, which has the highest rouge score. And rouge, very briefly, is a set of metrics rather than just one. It's a set of metrics rather than just one. And we actually, the most common are rouge 1, 2, and 3. You normally use all these three together combined. So rouge 1, we will be measuring the match rate of unigrams between model output and the reference. So between basically what is our ground truth, what is our prediction. So we'll see how many words are matching. And so we also have rouge 2 and 3 that will use bigrams and trigrams respectively. So this is the classic original sentence that is used in NLP, which actually contains all the we basically is normally used. So the quick brown fox jumps over. Yeah, it's not finished because it should continue. Unigrams, just getting the word singularly. Bigrams, just get bigrams of the word, and trigrams. So after we do this, we actually check the matching between our prediction and everything that is in the abstract and everything that is in the ground truth. And we'll see how close they are. The closer they are, the higher is the rouge score. And so what we do at the end, we'll have input text, our input, and the targeted output. And in order to calculate this, we'll just put something called the mask token. So we will just remove, in this case, the blue piece for the text, and this will be replaced by a token called mask. And so the job for the network will be to find the best word that actually are replacing this mask token. And yeah, once the pre-trained model, in this case, actually, we can pre-train million, also like a billion of documents without any problem because everything will be automated. So we don't have to read everything. No, they're not manually labeled, but they are actually extracted using, like I said, this kind of rouge metrics. The higher is this, the more the more likely is that the sentence will be used as the target. Because the main point is training billion and billion of documents without a person going like reading through all the documents and try to get with the summary. And so yeah, and these allow the Google developer to basically train on almost 2 billion of different text. But how is the reference for you? So the reference for every sentence in the text, every sentence or paragraph here, basically we is actually compare. We actually try to get the rouge. So at the beginning, you'll have multiple, let's say, all the kind of sentence will be an hypothetical rouge. So when we train the model on the summarization, and we try to train the model on every kind of possible rouge, we'll just retain the one which has highest score. So it's kind of two different training. The first one we will just train using all possible rouge. And when we do the prediction, we just see which one works better for that text, and we'll just keep that one if we want to use one. If we want to use more than one, we'll just get the top two. So again, it's kind of is one training to extrapolate the right rouge, And after is another training to actually calculate the summarization. I don't know if hopefully it was clear, Willem. And yeah, so once we've done this kind of two different training, we have our model that is able to extrapolate from a text a summary, and we can fine tune. So fine tune, we will reuse the knowledge on our specific task. And the real power of our model is that we actually, even if we use a very small amount of examples for the fine tuning, like 1000, for example, we can get still a very high Rouge score, Rouge metric. So it's actually in some case for some for some data sets, the score that we reach on our fine tuning is actually greater than the previous score that was reached on that data set using other different architectures. So here you can see how powerful it can be if actually you have a very robust knowledge. But by the way, here, so also the number of the example will be also based on your task. So if your task is kind of general, because the train was already, the model was already trained on something general, you will not need a high number of example. If you have a very, very specific task with a completely different vocabulary, think about some, like, I was working with on a project that was like chemical, it was about like chemical elements and stuff. So, but sometimes you have to find a very specific model that is trained on that specific like corpus of words. Otherwise, you could get a kind of, it will not be matching with all the relation that has been like extrapolated by the transformer because it's completely different corpus. But the biggest power of Pegasus is again that if you are lucky enough, and there are like so many companies, many also people who have access to very big servers, very big GPU, they actually can train Pegasus on different data sets, different tasks. So actually you will find probably, if it's not Pegasus, maybe something else, you will find something that you can use for fine tuning. Because again, training something from scratch, if you want to get something very robust, it's gonna take a lot of time, a lot of money. So this is the last slide. And just again, write something in the chat if you have any question. So what I'm gonna do now is showing the Jupyter notebook that I prepared, where we're going to do a translation fine tuning. And I got this from Hugging Face. So here is the Remco, yeah. So it's basically your Hugging Face questions ready to. What does fine tuning look like? Document. Yeah, no. This is supervised. It's always supervised. So if you use something pre-trained that was supervised, you have still to go with supervised. But like I tried to say earlier, there is also a way to get from unsup to get a train to create the label for something that doesn't have a label. So again, root score, or again, if you don't want to waste too much time, you can also get like if you know that, for example, in a document, the introduction can be the summary, you will always the introduction, and you will start training the model and see the results, changing the label and see how it improves. Because at the end, machine learning is very like trial and error process. You'll never know if something is going to work until you don't try. So now I have to stop presenting and I have to share my screen, I guess. Yeah, so let me know if you can see my screen. Actually, let me just put Teams also for some question on the screen. Okay, so basically, I posted the article as well from Medium, so you can have a look if you want. So like someone said, there is the Hugging Face. Basically, is one of the most popular and robust community for AI. So you can find here ready to use models, and the also extremely detailed. So you can see tasks. So basically, you can use a model like summarization in this case for every task. If you click on the model, you can also get, for many of them, you can also get the code, how to use it. I was something from, the G, maybe let me see this one. Yeah, you also get the Python code to use it. So it's very like 10 minutes, not even like, probably not even 10. So to use a model that is pre-trained was from someone on some other topic, you can actually see how this model is performing. You have a lot of different choices, lot of different as well data set you can see here. So it's a very, 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 very good kind of environment for all like AI interested people. So let's see how it works here. So okay, what we want to do, we want to retrain a model that for like Italian English translation, and we want to retrain because apparently, so what it has already is trained on very some like common text, and we have some text. We actually were able to extrapolate some text from a parliament session. So this is a kind. It can also contain some very detailed words that probably they're not contained in a kind of like common corpus that the model has been trained on. So we want to like fine tune all this knowledge on our specific task. So just for this purpose, we'll just get like 100 different data points. So 90 will be the training and 10 will be the validation set. We use a metric called SACBLE. It's very, very similar to Rouge. So it basically, what it does, in order to comparing, and also here there is all the kind of documentation. So let's try how it works. So in order to comparing the words, it's just comparing basically the unigrams, bigrams, and trigrams all together. So as you can see here, I have the same sentence. I get like 100% score. But if I just change, for example, this there, I will just move somewhere else. The score is definitely a lot lower because, again, this is not just the context, but also how, using the order of the words is just trying to get out if the meaning is the same, let's say. So first step, we have to download something called the checkpoint. So a checkpoint is basically what the model has been, the output of the already trained model. And so we download this from iKingface. When you download the model, you also have to download the tokenizer, let's say, model for that. So basically, tokenizer is how, because we normally have raw text sentences, how we are going to split that sentence. And so normally this task will be, just basically split. You get all the words, you just remove the space, and every word will be a single token. But here is very, very different. We use something called sentence piece. So basically, this is a task called subword tokenizer. So it's not that we are not considering a wall of word, but it's more like a character-based tokenization. So in order to do, because we want to do this, because so common words, they normally get a slot in vocabulary. But the problem is that when we have like unknown words on rare, we don't have a fair representation of these words in our vocabulary. So doing our subword tokenizer, we can actually try to make also this word, make them, let's say, important. And I will show you how it looks like. It's also extremely fast because it's implemented this in C++, is white space agnostic. So same difficult to train a model in English like Chinese and Japanese. So for example, let's try to tokenize hello, today is a nice day. Normally will just be hello, today is a nice day. So like 1, 2, 3, 4, 5, 6 different, removing the comma, it's going to be just 6 different words. But in this case, as you can see, we're not tokenizing by word, we're tokenizing by, let's say, chars. And in order to understand how to select a char, these are just the most common chars in the kind of in the vocabulary. So for example, from hello, because there are multiple ways that you can actually tokenize hello, you can have HEL, HELL, or just H and E. So based on the count of these sub words, we actually decided tokenization. And this, as you can think, you can actually reuse the token for another word that ends, I don't know, in ELLO. So it's a very reusable stuff. I will, again, every token, there is a vocabulary that I will show you now. Every token has an input IDs, and this, remember, is the attention mask. So at the beginning, it's just 1, 1, 1, 1. But based on the training, these weights are going to change. Now, just to show you how the vocabulary looks like, if I can find, just 2 minutes left. I think I can do it. So this is how the vocabulary looks. Sorry. Okay, this is how the vocabulary looks like. So from every, this is just the encoding. So this is the real word. From every kind of group of charts, there is a specific IDs. So for example, from the letter H is 224. So if we go here on 224, we will see that is H. Again, in this way, you can reuse a lot of token, and you can have a lot of words. And because actually it goes down to a byte representation, it actually is incredibly fast. So for example, in this case, the vocabulary contains 8,000 words. So yeah, so when you tokenize, you have the input ID, you have the attention marks. There's also a way to tokenize like batch sentences, and I just did this to show you the padding. So if we have padding true, everything is gonna be padded to the longest sentence. So for example, hello, today is a nice day, has this length, and where 0, this is probably something that Rory asked earlier, 0 is our end of the sentence char. So instead of end of the sentence, we just get like /s. So at the end of every sentence, we'll always be adding something like 0. In this case, we added yes 0, but because we want to pad, we add this other char that is 80,378 is the last char. It's basically just like used for padding. So as you can see, everything is very well structured, and basically understanding everything will give you basically all the answer for how it's working behind the scene. So what we do, this basically is a function just to pre-process all our input, and our train will look like the input IDS that will contain basically all the input IDS for every of the data point, and at the end we'll get the attention mask. So when we train, this one will be changing based on the context, and after the one we also have the labels. So just to show you again how this looks like very quickly, if I can. So if we do df.train, so basically you have the translation that contains the English and the Italian version, input ID. This input ID are referred to the input that is English. The attention mask, actually this is Italian, sorry. So the input is Italian because it's it English model. Attention mask, and also the label that is the input IDS specifically of the sentence resumption of the session. So there is also, I'm late 1 minute. So there is also, let me just see, yeah, there is also a specific way, because this comes from Hugging Face. There is a specific way how to shape the data set. So you will have something like this. This is a data set structure that contains features. So all the columns, number of rows. If we want to print one row, it just looks like a dictionary containing every different features in this case. So translation, English to Italian, input IDS, attention mask down here, and label mask. So again, for the fine tuning, we'll be using the trainer API, the training API, and sec-to-sec API. Actually, the trainer and the sec-to-sec API. So these are all like functions that you can actually have a look at on how they are used when actually I'm going to share with you all the code. The important one is sec-to-sec training arguments. We basically just do all the learning rate. We just can set different arguments, different stuff. Because so when you do a pre-trained model, you're actually using these. We are just going to keep the same structure. We are just going to change the evaluation metrics. In this case, is the strategy, the learning rate, how much which batch size we want. In this case, 16. Weight decay, number of epochs, and so on. So, yeah, we also need the data collator to pad the input to a maximum length. So a maximum length that was established at the beginning. And yeah, this is actually to compute the metrics later. And yeah, you do the trainer. This is the trainer API in this. We basically use PyTorch, but it's also available in TensorFlow and like TensorFlow.keras. So the trainer, and basically this is, I cannot replicate the trainer yet because it actually takes 1 hour. So this is how the chain looks like. You have the validation loss, the blur. So the higher is the blur, the better is the score. It means the closer will be with our like ground through. And these that I've not found a lot, honestly, any documentation that this should be the generator length. So how many words we actually calculate more or less than the actual, than the real label. So if we are predicting like more words, then there should be or less words. So in average, we are predicting 29 words wrong. Yeah, so you see all the running evaluation here. You can save the model. And so in order to use the model, you save your model. You can actually just load it, both the tokenizer and the model. You actually generate the prediction, and you use this which will skip the special tokens like the pad at the end to refine the output, let's say. So this in Italian means that the government has kind of issued a new law. So let's see how this can be translated in English. Just loading the model can take time. So the government has enacted a new law. So as you can see, the model, even if it doesn't have any knowledge about what a translation is, because actually it's not understanding, but again, all the encoders have attention, is able to understanding all the words of the link, is actually it can also work definitely better than the Google Translate. So all these can be definitely the future for basically all tasks like summarization, like in this case, translation and so on. So we are at the end. I'm sorry if I took 5 minutes more than usual. I know it's very lot to ingest, but hopefully I give you, I don't know, by the way, do you have any kind of imminent word or something? It's 2, it's until 30, it's not 4, yeah. I mean, yeah, we can have, do you have any kind of word, a conversation, we can open a conversation on this. Do you have any kind of question or stuff? So all these kind of models, so this one is called Marian, is on Hugging Face. So again, just downloading a model, and you can train on your task and see how it works. Transformers, Lstm, yeah. So in theory, this is not completely true. So the Lstm and the gated recurrent unit, they were supposed to resolve the vanishing exploding gradient using memory gates. So just keeping information. But that does not work very well when we have very long sequence. So the transformers, compared to any other algorithm is existing at the moment, they perform simply better because of how they are structured, because of the training time, because of the input data. So they're simply better than that. So LSTM, something honestly that I did my dissertation on. When actually you're trying to extend a little bit, the memory gate doesn't work so well anymore. So now the transformers are extremely very common on text generation task, but like I said, you can also use on computer vision task, mostly for like image, I don't know if image classification, but for everything that implies a generation of something, transformer can be used. Like I said at the beginning, that we can use the transformers for music generator, image generator. So there are some nice website which actually they let you like create drawings, just like modifying the input. I don't remember the name. Modifying the input, the weights and all the stuff. You can actually create your own drawings that basically just like AI. You can create your own songs and so on. How is your sense of color translation? No, the translation is perfect. It's 100% perfect, this one here. And so we actually reached, of course, this is a quite also, again, is a very kind of very common task. But so as you can see, even like in this case, we just gave 100, and because it was already common, it was fine. But if it was something completely different, a different task, of course, you will need at least, I don't know, 1,000 or 10,000, because this Marian model is not exactly Pegasus. So it's just another transformers. So again, the main con of Pegasus is just like even reducing for the fine tuning, not having a very big data set is gonna work just fine. So will the training differ if you use a most encoder? By encoder will be fine. Oh, sorry, tuned for specific language. So again, the main structure of the transformer, it works fine as long as you have a very good data set to train on. Because the problem that they are mentioning now is if, for example, you want to use a transformer that has been trained on a kind of, let's say, Daily Mail or Wikipedia News data set, when you actually try to fine tune on such like low scientific publishing, it can have problem if you don't fine tune using a relatively big data set. I'm saying starting from 10K on. This is for Pegasus. Because if, again, the main problem is like fine tuning, yes, but it should be the task should have some kind of similar features to what the original trained was. So again, that is the main problem. But on Hugging Face, you can find so many different model. So it means that if someone else, for example, I'm going to use a model for some like nuclear related words, and using that, if you want to fine tune on that task, and if I wanted to use something that was trained on like Wikipedia News, of course, the performance will not be as good as the one that I will have when I'm gonna use like some pre-trained on a nuclear data set, nuclear data set. The intuition for which domains do better without fine tuning. So without fine tuning, you basically the task should be exactly what the original train was on. So for example, if for translation, again, if you use some like Wikipedia News, it will be on, if everything is on Wikipedia, it should work just quite fine. But of course, if you use this model and after you want to train on some like, I don't know, chemical law, very scientific language, I mean, it will give you some output, it will work, but maybe that can be used, for example, for a kind of POC just to demonstrate that it can work. But the performance will be definitely lower. So something I cannot give you some like specific number, but we are talking probably also about like an improvement of 10-20% if we have if we fine tune on something that is the same or something that is a completely different with the original data set. And so, okay, best productionized fine tune. Oh, this is nice questions. Tips can you give one? Yeah. So have handle with this on local. It's a bit of a pain because, for example, if you want to production something like this, okay, first of all, productionization will mean imagine a very big MLOps architecture. So everything will be automated, training, labels, relatively automated actually, training, labels, actually gathering data, labeling data, training data, hyperparameter tuning, and so on. So the best way production this, you should have a very well MLOps on the cloud, because again, so just for training, so for the example that I showed you earlier, I trained using 100 rows, basically 100 translation English Italian or Italian English, yeah, and it took 1 hour. So 1 hour just for 100. If you get like 10,000, it will be probably impossible. So first advice is you should have something that is set on the cloud. And so if we're talking about cloud, we have like Google GCP, we have Microsoft Azure, and we have the other one, AWS. And basically all of them, they already have something that is, let's say, pre-trained. So they already have something like ready-to-use service, like there is AutoML in Google, computer vision API in Google. So it's basically just a fact of you basically just upload the image or whatever it is, and you can just get the output. So that will be like very like no code at all. So again, productionize, you need to have a cloud, you need to have a very well setted stuff, because normally when you want to do something like this, it's you basically need to set, you know, all the pipeline and stuff. And first of all, you need to have a very good budget, because this can cost a lot. During one of my projects, the cost of training a model was around like 35-40K, and is quite high. So productionize, that basically will imply all different steps, cannot be done like locally. You need a cloud with all the steps, and again, for the fine tune, you can have your own custom model, or you can start. What I would suggest, you can start from something that is already there, some API, and you can see how this API perform on your task. Or worst case, you just use like a custom data set, but that will mean to really like code on the cloud, and it can be also quite hard. So hopefully I'll answer to your question. So if you use Prodigy, I don't know what Prodigy is. When does upskilling on the ops manual labeling? So the ops for sure, 100%. I mean, even now the funny stuff is that about manual labeling is that there are services on Google that is called labeling API, I think. But if you read the documentation, there is no API at all. They are just like human people which are paid to label images or text. So actually, it's for that when I was a minute ago, when I was trying to explain all the pipeline, I was saying that the labeling can be relatively automated, because again, to label something, you can also if you want to automate 100%, you should do another training for labeling, or you can use this service, but basically just like someone else labeling. But labeling is probably the kind of boring side of NLP. And considering all the community, all the web, all the stuff, for sure there is something or someone that has a data set close to what you want to do that is labeled. So there are some kind of repo, you can check Kaggle, you can check Hugging Face, you can check normal like Git. You can see kind of all the blogs online and stuff, and you can have a look. Because yeah, it's so when you start probably a new NLP task, starting from scratch, there's no sense because NLP now is extremely common. So you can always take, at least for the beginning, take something that has been done by someone else, and you can reuse it for your own task. Yeah, thanks for the link, Rory. I will definitely have a look. So I don't know, it's 10 minutes left. And sorry, I don't know why I thought it was 1 hour and a half, but yeah. But I don't know, do you have any kind of questions or because yeah, by the way, I'm gonna send to Suzanne. She's going to share with you all the slides, all the code as well. So again, just have a look at Hugging Face. Very, very easy to use. There is so much that you can learn from there. And yeah.
Cool. Is there any other additional questions? If not, then I would like to thank Nunzio for putting nights and efforts into this. I'm sure this took a bit of time.
Yeah.
You have raised the bar again, so well done. Thank you very much. Also, thanks to everyone who joined this session, stayed till the end. I hope you liked it. I hope this is a good platform for you guys to see new content and stuff that we really enjoy doing here at PA Consulting. Reach out to others. Make sure that you log on to the Meetup platform. We are scheduling a new session first week of May that will have a little bit of a different feel. More about that later. Suzanne will put the slides, the code, and the recording of this Teams meeting on all the various channels. And send out through the Meetup platform, send out a message as to where to find everything. All right, thanks again, wherever you are in the world. Have a great rest of your day, evening, and we'll meet again early May.
Guys, thank you so much for attending and yeah. Like I said, like they say, never two without three. So probably we'll see again. I don't know when. Always available for these kind of things. Very good to share the knowledge, and hopefully you've learned something new today. Thank you so much, guys, and ciao, ciao.